Welcome to a video lecture where we look at the Compton effect, the DeBroglie wavelength, and the Heisenberg uncertainty principle. This will take us to the end of chapter 29, and we will pretty much wrap up our quantum look at physics. So please make sure to follow along and read the textbook. And here we go. So we've looked at what happens when we'll say a low energy photon, something along in the range of visible light, ultraviolet light, interacts with an atom, and we have an electron is ejected and it's scattered off. In most cases, the photon is absorbed, and that's where that energy comes from. Now, for higher energy photons, i.e. X-rays, so that's the next step up in the spectrum, going from ultraviolet light into X-rays. So these are higher energy photons, and they're X-rays. When those hit an electron, what you have is the electron is ejected or recoils. There's a collision, basically, similar to momentum, where we have it's an elastic collision, and there's also the photon itself bounces off in some direction, and this is known as Compton scattering. We've talked about the energy in a photon, and this is determined by Planck's constant and the frequency of that photon. We also know that for the momentum of some photon, we have momentum is mass times velocity, and mass is the velocity of a photon is moving at the speed of light. And we can go through and we can rearrange these and combine these couple of things here to start to look at how energy, and combine this energy and relationship to how it is related to the momentum of a photon. And what we end up getting is that the momentum of a photon depends on Planck's constant divided by the wavelength. So for a very high energy photon, that means it has a small wavelength, it's going to have a lot of momentum. And this means that when a collision does occur, it has a higher probability of ejecting or shooting off an electron within an atom or something like that. So once again, the momentum of a photon, then this comes from the Compton effect, which we'll come back to in a second, depends on Planck's constant and the wavelength. One of the other consequences of this is that this shows us that light has particle properties because it has the ability, it has momentum. And so when something has the momentum and it's able to cause a collision, it's something that has mass too. In this case, a photon doesn't necessarily have a rest mass, but it has a mass due to the amount of energy that it has. So coming back to this idea of the Compton scattering effect, we have an incident photon of a high energy. It needs to be of an X-ray or higher on an electron, and this is able to scatter off that electron. And the photon also recoils at some unknown or known angle, in which we're not going to look so much at the angle aspect, but more the conservation of momentum here. And so that the momentum, or the conservation of energy, actually in this case, where the energy of the incident photon is equal to the total energy of the scattered photon and the energy of the recoiling electron. There's more that you can do here, where you can actually predict the angle and the concentration, more or less, or the probability that something will reflect off to that angle based on the incident X-ray, and actually use that material itself that it's scattering off of to determine that angle. In 1924, a guy named Louis Victor DeBroglie, and he reasoned that if particles and objects have a momentum, and for higher energy particles they have a momentum, so they have a wavelength, why don't all things and all objects have a wavelength too? And he didn't really put much experimental data into this, but he just kind of predicted and said that, okay, every object's going to have a set wavelength based on the momentum. Like, so if you have, for example, a baseball moving, a baseball has a small amount of momentum, it would have a wavelength that equals about 10 to the negative 34th meters. And that's a really small amount of for a wavelength. But it turns out that this is correct, and other people were able to do a lot of other experimental work with other particles, very smaller ones, but bigger than, say, photons or electrons and stuff like. They used soot or smoke particles, and they found that if you shoot these, if they have some set of momentum, you can actually measure the wavelength based on using a single slit or a double slit diffraction pattern and figuring out how far they diffract out, and you can actually measure the wavelength, and it turns out that this is correct. So in order to reverse the formula from the momentum is equal to Planck's constant divided by the wavelength, we get the wavelength is equal to Planck's constant divided by the momentum. So every object actually has a certain wavelength. It just happens that that wavelength is so small. For example, a car going into a tunnel has a set momentum. It has a wavelength. It will diffract as it goes through that tunnel, but it will diffract at such a small amount that it's not noticeable. But yes, it actually, all objects, no matter what, as long as they have some momentum, will have a wavelength. One of the basic things within what does that word really mean when we're talking about quantum physics? I guess it's more of one of the foundations of quantum physics is that we can't know, we have a limitation in how much information we're able to know. We are able really to know either the momentum or the position of an object, but never both. One of the two at the same time. And the more that we determine about one, the less we're able to know about the other. So as we get more and more precise about the momentum and therefore the velocity or the motion of a particle, it becomes harder and harder for us to determine the exact position of that said particle. So this really it's termed the Heisenberg uncertainty principle, and there's a full-on way that we can go out and calculate this. Quite honestly, there probably is going to be very little about this, or if anything at all, on the AP exam, but it's just kind of like a very cool idea. This is one of those formulas that I don't even think you have to worry about, but it's just it's a cornerstone within the quantum physics that the more you know about one thing, the less you know about another. Before we talked about every object has a wavelength and some momentum or whatever, that gave us the idea, oh, maybe there's some uncertainty that. Now, within those particular objects, as you get bigger and bigger and bigger objects with, quite frankly, less momentum than, say, an electron or something like that, this doesn't really hold true. But at a quantum state, it becomes harder and harder to know exactly where something is and where it's going. And this gives us rise to some of the other beliefs that as the idea of the electron cloud model, whereas before we thought that, the electrons orbit and set kind of nice little radius at a constant thing. It's a lot more kind of ambiguous in where the electron actually is, but we do know, like, for example, the speed or something that is moving around the atom, but we have a probability, we can predict the probability that it will be within a certain area. So from that, we're able to kind of solidify more of this idea that there's a cloud of electrons around an atom or a molecule, and that is really what the important thing is. Within a reasonable doubt, we can get a prediction to where that, we can have I would say a certainty to where that electron is around an atom. 2 questions tonight, actually, well, 3, but 2 topics for the questions. The DeBroglie wavelength we'll look at in class a little bit more. So first, Compton effect. When the X-ray photon scatters off, an incident X-ray photon scatters off from the electron, does the scattered X-ray speed increase, decrease, or stay the same? And I would like you to also explain why. So I'm going to put these up as multiple choice questions on the online, And I'd like you to actually explain why afterwards. Just a quick little sentence. And second, when the X-ray photon scatters from the electron, does the wavelength of the scattered photon increase, decrease, or remain the same? And explain why again. And last, the speeds of an electron and a proton have been measured to the same uncertainty. Which one has a larger uncertainty in position? And I'm going to put multiple choices for this one up online too, but I want you to kind of think about this. Once again, you'll have to explain why. So this really wraps up our look at quantum physics, which is confusing to say the least, or non-intuitive, I guess would be the best. It's non-intuitive to say the least. And we'll try and move forward and move into a little bit more of nuclear physics, but I hope you enjoyed our little segue into this. I'll see you tomorrow in class. Have a great afternoon or evening, whatever you find yourself watching this video.